I want to introduce Robes Parrish, who will be our next presenter. Robes is a hydrologist with the U.S. Fish and Wildlife Service Mid-Columbia FWCO office in Leavenworth. For over 16 years, Robes has worked primarily on habitat restoration, project design, analysis, and implementation throughout all of the subbasins of Central Washington. He enjoys trying to unravel the complex and often unseen interactions between surface water, groundwater, and the species that depend on them, of which we'll hear about water in different ways today. Although more commonly found doing the useless sport of rock climbing, I understand that one. He's really looking forward to fulfilling his bucket list trip, paddling down the Grand Canyon this fall. I did that 2 years ago, and it is amazing. You're going to love it, Robes. So without further ado, I'll let you unmute yourself and I will let you take it away. We can see the presentation. Everything looks great.
Cool. And you can hear me well?
Yep, you sound great.
Great. Well, thanks again for the intro, Nicole. I guess I'm the next best thing to Sleeping Lady since my office is literally within spitting distance. So use me by proxy, I guess, everyone. Yeah, as Nicole said, I'm a hydrologist with the U.S. Fish and Wildlife Service in Leavenworth, and I typically actually work mostly on river restoration projects. But as part of my job, I tend to track climate and snowpack and hydrology since it affects a lot of what we do. And I've given this presentation a couple of times to some of our local watershed groups in the Upper Columbia this past spring, and so I was asked to give this with a little bit more of a statewide focus to you all. So hopefully this is interesting, and let me get started. Let's just, there we go. So before I kind of dive into the meat of what I wanted to talk about, I just want to highlight something that I think is important for you all to know, because throughout my presentation, you'll see a lot of metrics, things that are shown kind of in relation to a normal or a baseline period of record. And that's true for a lot of stuff you'll see, primarily temperature and precipitation, some of the most important variables we'll talk about. But this past May, last month, there was an important change just to be aware of. The World Meteorological Organization actually uses a 30-year baseline period for what they compute normals to. And so that was recently updated, it now being 2021. The new baseline period is now from 1981 to 2010, as you'll see here in this slide. So the previous one was 1991 to 2020. And so what that meant for us, that shifting baseline, is that we now have a mean annual temperature that is warmer than the prior 30-year period. So that shows up in a lot of different ways. And that's true for most of the United States, as you can see. Precipitation is a little bit different in that we have a bit more of a mixed bag, at least in the Northwest, where you'll see precipitation increased in the most recent 30-year period, particularly in the Olympics and the west side of the Cascades, but is actually a little bit drier, as you can see there east of the crest, certainly a lot drier throughout all of Oregon. So again, you'll just see some different baseline periods that I've tried to note on a lot of my slides. So just kind of keep that shifting baseline in mind. And you know, that's really been true for a much longer period of time, really. We have a pretty consistent trend when you go back to about 1895, when observational records were really first taken and considered most reliable. And you've seen within the state about a 0.2 degrees Fahrenheit increase in temperature over that same time period. So we just continue to shift that baseline upward. And if you dive into the actual meat of the data, it's interesting to note just that the month by month, the January and September monthly average temperatures actually show the greatest increases statewide. So there's a lot of interannual variability there. Sorry, intra-variable variability. So anyway, let's just take a quick look back at the winter and spring that just passed, and I'll kind of give you the top line sort of weather story that many of you probably saw in your own part of the state. And I think that this graphic pretty well shows what I think is the principal storyline, and that is these arrows represent the landfall location of atmospheric river events going back to early October. And an atmospheric river is just a thin ribbon of very, very juicy moisture fetch that often stretches back into the subtropical or the tropical Pacific. You know, think of this as the Pineapple Express. And so over the course of a year, we actually receive a huge proportion of our total annual precipitation via these relatively short-lived but really juicy atmospheric river events. And so throughout 2021, you can see that the landfall location for almost all of them was directed at Washington and Oregon, with very few headed further south down into California. This is only updated through mid-February, but as you'll see in later slides, that pattern still persisted for much of the rest of the winter. And you can contrast that with what we saw in 2020, which was a much more even distribution of these atmospheric river events up and down the coast. The other big weather storyline, I think, for the winter to note is that we were in a moderate La Nina event. And so the purple line, even though this only goes through, I think, the middle of April, where you see we dropped below the La Nina threshold, which was negative 0.5 degrees Celsius. And it's been trending back up here into neutral territory ever since. And you'll see this slide again at the very end of my presentation, but just note that for now, the winter of 2020, 2021 was characterized by this moderate La Nina event. Another big hemispheric pattern that climatologists like to use to describe some of the forcing mechanisms that go on is the Arctic Oscillation. This is essentially you can think of it in both this negative and this positive phase, as you can see in the graphic there in the bottom right. A negative phase is essentially the polar vortex, and that gets talked about a lot. What that really means is that there is a wavy pattern to the jet stream, so a lot of those storms are emanating, cold storms are emanating from more northerly or Arctic locations, and they drop quite a bit south into the lower 48. Whereas the opposite, with a positive phase, Arctic Oscillation is a much more east-west aligned jet stream, and that cold air stays bottled up in the Arctic. So if we look back at the winter of 2019, 2020, you can see there that the very, very high peak that we saw was actually the highest value for the AO going back to 1990. So, you know, that meant that we had a lot of cold air bottled up in the poles, whereas this winter was a bit more of a mixed bag. You can see it was closer about the mean, so not quite as strongly influencing our day-to-day weather. So what did all that mean in terms of climate? So this shows the average temperature departure from average using that 81 to 2010, so that older baseline I talked about. But nonetheless, across the Western United States, you can see a lot of green and yellow for the most part. So going back to the start of the hydrologic water year up until the end of May, you can see that at least along the West Coast that things were generally warmer than normal. And you don't really get into cooler than normal conditions until you get about east of the Continental Divide. And overall, the contiguous US ranked 5th warmest since 1895, so for the entire lower 48. And then for the precipitation story, you can see that it was very, very dry throughout most of the West, which, you know, we're sort of blessed, you can see in Washington there, and that we're one of the only locations in the Western US that actually saw above normal precipitation or even near normal precipitation, with some pretty significant deficits as you get into the Southwest, the Four Corners, and California especially. And really this is inclusive of what would be this period, this March and April that we just passed was extremely dry, as I'll show you some more graphics about. So the fact that we wound up close to normal or even a little bit above normal is still a little bit of a gift, I suppose, because we had the record driest March and April period for Idaho, the second driest ever for the state of Oregon, third driest for Montana, and the fourth driest March and April for Washington. And again, those are records that go back to 1895. And if we zoom in to our state a little bit more specifically here, the scale is a little bit different, but you'll see the pattern of course is the same. So you've got a very, very dry, or sorry, very, very warm period that was experienced in the Columbia Basin. A bit more of a mixed bag throughout the rest of the state, with the only area kind of cooler than normal being up toward the San Juans. So, you know, not too terribly, not a massively abnormal year unless you're in the lower Columbia Basin. But precipitation, you can see much more clearly had a very dry period throughout the entire Yakima Basin, most of the Columbia Basin, and extending up into northeastern Washington as well. So sometimes 50% of normal precipitation for the period. And if we zoom back out and look at those in terms of the springtime only percentiles, you'll see that, again, much of eastern Washington experienced the record driest February through May period, whereas things got a bit better as you went into the Cascades and even over into the Puget Sound, but below normal conditions, or much below normal, sometimes in the bottom 10 percentile throughout almost all the Pacific Northwest. And unsurprisingly, that's led to drought. And this drought obviously extends pretty much everywhere throughout the western US, little portions of our state being the only exception, maybe with western Montana, northern Idaho there alongside us, but really some pretty significant drought conditions as of, well, currently. And it's interesting to see how this has progressed, because 2020, we ended the year with 41% of the United States in drought, with 18.6% in either extreme or exceptional drought, so the two worst drought categories. And that really only expanded in 2021. So as the year is drawn on here, we have 53% of the US in drought and 26% in extreme or exceptional drought. So really some pretty remarkable statistics when you look at it across the entire country. So taking a look at what the precipitation curve looked like, again, going back to the beginning of the hydrologic year, so October 1st, 2020, you'll see that starting over on the peninsula here in Forks, the red line is the observed precipitation, the black line is the median. So they tracked pretty close to the median throughout the winter time, but things started to dry out as we got towards spring. Mount Vernon, sort of the same thing, although they did a little bit better in the springtime, but you'll see the red line tracks pretty closely to the black line throughout most of the year. But things were a bit drier as you got east of the Cascades. So here is a plot of Winthrop, and you can see that they did very well through most of the year until mid-February, when the spigot really shut off, and that line just going horizontal there owes to what a dry spring it's been, to the point where they've now wound up a little bit below normal in terms of cumulative precip for the year. And then further east, as I mentioned, the Columbia Basin and the Palouse have been exceptionally dry, and you can see that here in Moscow, where things went dry starting in about mid-February and haven't really received very much precipitation at all until this last event, the last couple of days here. Same story down in Kennewick, where we had short periods where they accumulated a lot, but then owing to that late winter dry spell, the line just kind of goes flat from that point on. So below normal overall for the year at this point in the Tri-Cities as well. And then taking a look back again at temperature over the entire time frame here. So I think this goes back to 1978, 79. And you can see that there's a pretty clear increasing trend for the entire state over that time frame. We've been increasing by about 0.3 degrees Fahrenheit per decade. And then, you know, the frost-free growing season is sort of another metric by which we can look at how that manifests. And you can see, again, a pretty clear increasing trend line for the entirety of the state, increasing almost a week across that whole period of record, 1979 to now. And then that situation is made even a little bit more clear when you, or stark, I guess, when you look at individual stations, not just statewide. So here's a plot from Winthrop where you can see that the length of the frost-free growing season has extended by almost over 2 weeks in this time frame here, with much of the recent decade being among the warmest and longest growing seasons that they've experienced. Not quite as dire down in Yakima, but again, increasing by about 8 degrees per decade, or 8 days per decade. Pretty strong, clear trend line. And when you parse that out a little bit more, you can see that is obviously made up of both when the last date of freeze occurs in the spring and when the first date occurs in the fall. And they're pretty evenly split. So you can see statewide, we've been increasing in the spring by gaining about 3 degrees during that growing season and then you've got about 3.7 degrees in the fall. So really kind of increasing the tail on both ends. And that's really no surprise to anybody, and this has been very well predicted by the models, the climate models, for quite a long time, really. I did a little bit of a look at what that has meant for individual sites. So this is for Wenatchee, and you can see that the climate modeling has shown that the last freeze date on average would be expected to occur on March 13th in the mid-2020s here, and the date of the first freeze to occur by October 26th. And this is under the RCP 8.5 climate model scenario. So if any of you are familiar with those models, that particular scenario represents the worst case scenario. And interesting to note that already here in 2021, the dates that are shown there that were predicted for Wenatchee, we're already hitting that. So to me, the take home seems to be that at least at this particular site, we're already well on our way to experiencing these extended growing seasons with the date of last freeze and first freeze occurring both earlier and later in the year. And now just taking a look forward for the rest of the summer, we've talked a bit about what the year past has looked like, but going forward, this is the North American multi-model ensemble. So a whole bunch of models averaged together, and what you can see is that for July, August, and September in Washington, most areas, especially east of the crest and northeastern Washington, are expected to be above normal for the entire period, although the Cascades and the Peninsula and the West Side actually do currently have an increased likelihood of experiencing normal temperatures through that period using this model. That same model also predicts precipitation, and you'll see that it's shown to be drier than normal for the July and August timeframe, and things maybe get back to a bit more normal by September. Worth remembering, though, that summertime precipitation for most of the state is really not much of a big deal. So we're not talking about huge amounts here, but expected to be a dry summer. And a different way of looking at this, backing out to the North American level, for June, July, August, you'll see that everywhere across the Western United States is expected to have increased chances of above normal temperatures in the plot on the left and drier than normal conditions in the plot on the right. So that band of drier than normal extending northwest from Washington down into southeast down into New Mexico. And then going forward into the next period, the September, October, November, early part of the fall, still very or elevated chances for above normal temperatures throughout the entire lower 48 and Alaska, with drier than normal conditions expected through portions of the West in through the Rockies and the Midwest. So what does the winter just past look like in terms of our snowpack? What's up in our bank up in the hills? So April 1st is the date when hydrologists typically take stock of how much snowpack you've accumulated, because it represents sort of the median date when snowpack is at its greatest extent. Obviously that varies by location and elevation. But as of April 1st, 2021, you can see that Washington wound up quite a bit above normal in terms of its snow water equivalent. So if you melted down all of that snow into liquid form, how much water would that translate into? And you can see that we were quite a bit above normal throughout all of Washington, portions of Oregon as well, closer to normal as you went east into the northern Rockies, but then things turning more yellow and orange as you get further south into the Rockies and California. California itself, though, you'll see, you can notice, is conspicuously absent from this. So this is the NRCS SNOTEL network, and NRCS doesn't maintain the SNOTEL network in California. They do their own through their cooperative snow survey. And you can see on the left, as of April 1st, the northern Sierras were really at about 66% of normal, with things getting even worse as you went further south, 42% of normal in the southern Sierra. But then only 3 weeks later, you can see things had melted dramatically. So things came off very, very early, 36% in the north to already only 18% of normal in the south. But going back to Washington now, here's what it looks like zoomed in at our statewide level with the central Puget Sound and west of the crest really doing very, very well, sometimes up to 50% of normal snowpack. A little bit less so as you get east of the crest, but overall a very good accumulation year, with only the far northeastern corner of Washington towards Spokane being a little bit closer to normal. So this is good. This is a good insurance policy for our coming warm summer. That's interesting to contrast with last year. So here's April 1st, 2020, and you can see that the overall picture was still pretty good throughout most of the state, with only the upper Yakima Basin being a little bit below normal, but not quite as much so. So we did better here on this La Nina year than we did in 2019, 2020. That's actually in reverse. If we look upstream into the Columbia River Basin and the Fraser River Basin, so this is a a map of accumulation in British Columbia. And what you can see is that as of April 1st, 2020, they were doing very, very well up there, sometimes up to 23% above normal snow water equivalent. But then this year, they were a bit closer to normal. So while we wound up quite a bit above normal, they were closer to normal looking upstream there, with the exceptions being up on the northern Coast Range. So for those of you living in the Columbia Basin, this is obviously important in terms of what you might see coming down the river through the summer and into the fall. So looking at a couple of individual SNOTEL sites around the state, just to give you a bit of a perspective on what those accumulation patterns look like. So if you follow the black line, that would be the accumulation curve so far. I think I did this as of last week. The little green X is the median peak snow water accumulation date. The green line itself is the median curve for that 1981 to 2010 baseline. So starting here over in the Olympics, you can see that they wound up quite a bit above normal with a near normal peak and have experienced a pretty typical decline so far. Going into the North Cascades up here at Hart's Pass, again, quite a bit above normal, although it may have peaked a little bit earlier and started to run off owing to that dry spring again. Moving south down towards Stevens Pass, very good snowpack through much of the year, and it actually extended into the spring. There was enough cool temperatures that we didn't begin to lose our snow until later than that median date. And a similar situation over at Stampede Pass. This is effectively Snoqualmie Pass, but above normal snowpack and near normal peak accumulation date. And then south down toward Mount St. Helens here at the Lone Pine Snowtell site, you can see that they peaked again above normal with a near normal accumulation peak. And I showed it on a map earlier, but really the only exception to our above normal snowpack was up in northeastern Washington. So here's a site up there. This particular site wound up actually below normal, as you can see for the year, although it peaked at normal. But there's a lot of local variability between stations. So, this may not even be representative of all of northeastern Washington, but it's worth remembering that there's a lot of local factors that influence accumulation throughout any given year. So it's worth averaging these things across an entire basin and not just looking at a single site. And then lastly, down into southeastern Washington, you can see this Spruce Springs site, again, was above normal snowpack and a near normal peak. And pretty rapid decline as we experienced this warm spring. So they're out of snow already. And when we look back again to last year, and you can see a better distribution of snow owing to those atmospheric river events being a little bit better distributed. But from April 1st to June 1st, what you see is everything transitioning from greens and blues to reds and oranges very, very quickly. And I think that it's important to just remember that no matter what your accumulation has been for any given year in the mountains, things can change fast, and a warm spring can really alter an otherwise pretty good runoff forecast. And it's also worth remembering that too from a longer term perspective in terms of how we measure stream flow. And because a lot of the data that is fed into the predictive models for stream flow in many areas is based upon snow water equivalents measured at these snowtell sites. In our current climate, we've got high, mid, and low elevation snowtell sites. But as the climate warms into the future and those lower and middle elevation sites in particular start to experience more and more rain and less snowpack accumulation, the data that informs those stream flow models is inevitably going to change as well. So our ability to predict future stream flows would be reduced in this future scenario. So there's a lot of different folks that are looking at ways to mitigate for this, looking at different types of sensors that you might use, things like soil moisture, but really having to reevaluate how we predict stream flow in this climate moving forward. So what did all that mean in terms of our hydrology and stream flow? I just took this screenshot from last week, so not current as of today, but you'll see that most of the state was near normal, those green dots in terms of the median flow for the date, perhaps even a little bit below normal. So, the last week or 10 days has been a bit cooler than normal, which has been really pretty nice, I know, for a lot of us here. But if we forecast forward, what does that mean in terms of predicted stream flow from the Northwest River Forecast Center? You can see that looking at the entire basin or all of the Northwest, you can see that things on the west side are expected to look pretty good with lots of greens and blues for this April through September timeframe, and drier as you get further east, and very, very dry conditions or low stream flows predicted for portions of Oregon, especially the Oregon Coast Range and the central Idaho mountains as well. And then in terms of individual hydrographs, if we look at the prediction currently for Grand Coulee Dam, so the Columbia River at Grand Coulee, again, focus on the black line and the green line, and you'll see that the current prediction actually shows reduced runoff expected from June through September. I'm guessing this is perhaps due to them holding back a little bit more water for some storage, although I don't know specifically, and really not getting back up to near normal until you get out into the early fall. And further downstream, sort of the same pattern. You can see here's the Columbia River at Bonneville Dam, and you can see that there's expected to be reduced stream flows for that period, and not getting closer back to normal until late in the summer, August, September timeframe. The Snake River itself, again, below normal stream flows expected until at least the end of July. And I'm not sure that there's a ton of storage in the Snake, but that could have something to do with it there. But the Yakima River is sort of the goofiest one of all. I'm not sure if any of you are down that way. You'd be very familiar with this because this is a classic flip-flop pattern in terms of how they manage the Yakima River basin there, where you actually get high flows during the summertime. So that goofy looking peak that you see later this month, and then staying elevated through the summer months so that they can deliver water to irrigators and users throughout the Yakima River basin, not turning off until later in the summer. And here's a neat tool that I just wanted to kind of point out that I've often looked at the beginning of every year, and you can kind of go back and see how it actually played out. But the Northwest River Forecast Center also puts out this plot where you can actually look at how La Nina, El Nino, or just ENSO for short, those phenomena actually affect historical stream flow peaks over time. So the orange line would be anything above flood stage. So if you look at the upper left quadrant, you can see that at least for the Methow River here in Pateros, that of the years where they experienced the greatest flood peaks, most of them occur on La Nina years, and really only one year, 1983, did they experience a big peak during an El Nino year. So they don't have this for every river around the state, but you can look at these for a lot of different sites that may be of interest or nearby to you. So taking a quick look at what this all looks like in terms of soils. And you can see here that as of June 9th, last week, everything, as I've said, was very dry throughout all the Western United States, sometimes into record dry conditions, especially in California. And that's changed quite a bit in our area, which, you know, you look at this period going back to March 31st, and you can see that we had done pretty well prior to that with the winter accumulation, but things have really dried out in the Northwest during that time frame. And that's kind of what we see today. So we've got very dry historical conditions, or relative to historical conditions. This is the Quick Drought Response Index, or Quick Dry. So it's really a 4-week indicator of drought, an intraseasonal indicator. And you can see the Columbia Basin and most everywhere in eastern Washington, very dry conditions, a little bit better off on the west side and over toward the Puget Sound and Esquim, but for the most part, everything east of the crest is very, very dry right now. And another way to look at that is using this satellite-based measurement. Again, all of the west, very dry, a couple of little blue splotches where there are exceptions, but in looking at how this shallow groundwater looks, and you can see just very, very dry, poor conditions throughout all of the Northwest at least. And that's led to drought, as I've been describing. And you can see that as of June 8th, so a week ago now, we had 92% of the state of Washington experiencing drought conditions, with 45% being in severe drought and 22% being in extreme drought. So really a pretty remarkable turn of events, given that we had such a good winter for most of the state. And you know, it's worth keeping in mind too that prolonged droughts, and not just a one season drought, but a multi-year drought, can really initiate a positive feedback loop that can be pretty damaging for lots of different folks and ecosystems. And so the classic hydrology model that you can see there on the right is influenced by this, by dry soils that accumulate over a number of years really influences how that vegetation responds. So dry soils translates to dry vegetation. In turn, you get reduced evaporation and transpiration, and then you get more surface heating. So when there's not the cooler vegetation there, the sun's power is increased at the surface, and that warms the lower levels of the atmosphere, leading to lower relative humidities, reduced cloud cover, and that further exacerbates drying and heating at the surface. So, as we look at the Southwest and California in particular, you'll kind of hear a lot about this in terms of their multi-year droughts and how that influences wildfire behavior especially. And let's talk a little bit about that. Fire. Here is our typical fire season progression throughout the Western US. So in June, the Southwest really peaks prior to the onset of their monsoon in July, whereas that's the time frame when we are really starting to dry out typically. So most of the Northwest experiences their peak fire season in late July and August, and that period of drying kind of moves northward in through September and the early fall. So Northern Rockies, those areas begin to burn in August, and sometimes we experience these fall moisture events that start to, or that can end the fire season as we get into September, but not every year. And the current wildfire outlook for the peak fire season here, July, August, September, you can see that we are currently expected to have above normal, we've got above normal potential for significant fire behavior throughout most of Washington during this 3-month period, with the only exception being the Olympic Peninsula and the Puget Sound, but also lots of places throughout the Southwest, California, and even the Northern Rockies experience or expected to have increased chances for above normal fire behavior or fire potential. And this question comes up a lot in some of our local watershed groups, but does a low snowpack accumulation year or a dry spring always lead to a bad fire year? And I haven't been able to find any peer-reviewed literature on this. If any of you have seen that, feel free to pass it along, because I think it'd be interesting to see. But what I did find is that the National Weather Service in Spokane did an analysis 2 years ago where they looked at this, and they actually found that neither one of those two things correlated very well to the total number of acres burned. In fact, they found that the thing that influences our acreage burn in a given fire season most strongly is actually May through August temperatures, followed by the number of lightning strikes or the number of lightning events that we actually get. So that kind of makes sense when you think about it, where everything eventually dries out. We lose our snowpack no matter what every year, and no matter how much we have, and it gets, if we get a lot of lightning events, then we tend to get a lot of fire. 2015 was a good example of that. They noted where we didn't have a very busy year until August 10th, when a very short duration pattern set up where we had a lot of lightning and a lot of wind, and that produced a huge acreage with 834,000 acres burning that year. And that's what you can see on this plot here. looking back to 1970. And obviously there's a pretty clear increasing trend statewide in terms of the total number of acres burned. But a lot of those happened in pretty discrete events. And as I mentioned, that 2015 Okanagan complex event was one of them. And even last year, which most folks probably don't think of last year as being overall statewide a terribly bad fire season, but you can see we burned the second most acreage in history. And a lot of that was driven by those Labor Day fires that all occurred during a lightning bust that happened then, and a lot of very, very strong winds. And we burned, I think, over 400,000 acres in that one period alone. And then nationwide, same thing. We've been seeing this increasing trend for greater and greater acreage burned every year. So this goes back to 1983. So in blue, you can see that increasing trend there. Whereas that's been happening even in spite of not having a very clear trend with the total number of fires burning every year. So the orange line you can see with that low R squared, not a lot of no trend to pick up on in terms of the total acreage, or sorry, the total number of fires, but a pretty clear trend with the total acreage burned across the Western US. And then lastly, I just wanted to talk a little bit about the ocean and El Nino Southern Oscillation conditions. Just as a quick refresher, El Nino Southern Oscillation is actually a phenomena used to describe what are actually two different physical effects. And so you can see in an El Nino year in that plot on the top, warm water is measured warmer than normal water in the equatorial Pacific, and it's closer to the coast of South America there. And then in a La Nina year, the reverse is true. So we have cold water that is near the surface and centered from the central Pacific east towards South America. Then there's also a concomitant geopotential height anomaly. So the high pressure, low pressure phenomena, in other words, you can see high pressure centered over the Philippines in an El Nino year and low pressure centered over the Philippines in a La Nina year. And so those two factors together, the warming or the ocean, surface ocean temperatures and the high-low pressure systems tend to drive winds and precipitation for much of North America. So that's why people pay attention to it. And since these are such big scale factors, these things have to be measured over a much larger range. So when you start to see, well, what do we consider this year? Is it an El Nino or is it a La Nina year? And they use the Nino 3.4 region as a means of averaging those things together. So that's that area you can see on the right in the Central Pacific. And this past year, as I said, we had a La Nina. So what does that typically bring? Well, colder than normal temperatures coming down on the north side of that polar jet and wetter than normal conditions in the Pacific Northwest. So the typical thought would be that we would have a colder than normal winter and a wetter than normal winter. So here's what was forecast from the Climate Prediction Center going back to last fall, the December through February, like the meat of the winter. They predicted temperature to be again below normal that you can see throughout Washington and the northern tier states. But what we actually experienced in that map on the right was only a small portion of Washington being below normal, whereas most of the rest of the state observed near normal temperatures. And then precipitation, as I said, they would have predicted based on past analogs for La Nina years, above normal precipitation. And we did get that in the mountains, and we did get that, as you can see in the map on the right, across Western Washington, but really near normal conditions as averaged over the rest of the state. These grid cells are pretty large, as you can see. So as we've been talking about, there's lots of local variability to this. But overall, you know, the going back to 1950, if you look at the map on the top, what you can see is these are, again, those geopotential heights, the storm tracks, so think of blue as a low pressure and think of red as high pressure. And those big pressures, domes steering the storm track. So you can see that in a typical La Nina event or a typically strong La Nina event on top there, we will get that stormier than normal condition emanating from Canada, driving down into the Northwest. But looking at the map on the bottom, we had from December to January, a period totally unlike that, kind of opposite in fact. And you can see that there was a lower pressure center centered over Siberia and over the Bering Sea, with a high pressure system or a marginally high pressure system centered out in the Central Pacific. In fact, this past December to January period was the least La Nina-ish pattern of all of the 13 moderate to strong La Ninas going back to 1950. So at least for that December-January period, things were not holding true to what they would typically expect. And when you look back at what was predicted, so this is from April 2020, and this spaghetti plot here, I guess, shows all of the different models, but if you focus in on perhaps the red, the thick red and the thick blue line there, the black line starting on the far left, so you can see this was made in April of 2020, but what they predicted from that point was indeed for us to descend down into La Nina conditions, so anywhere below that negative 0.5 degrees Celsius, and then climbing out of it as we got into the winter. That was the prediction as of spring of last year. But what we actually experienced, as I said, was a moderate La Nina event. So we went down to almost negative 1.2 degrees Celsius in that Nino 3.4 region last fall, and did slowly climb back up toward neutral conditions as we've gone here into the spring. So the models, I'd say, predicted the overall pattern very well, but they didn't predict the actual magnitude quite as well as you would hope. The springtime period is actually notoriously difficult to forecast from, though, to be fair. And this is just a different way of looking at the predictions going forward. So if you look at the gray bars there, that is the probability of a neutral ENSO event occurring. So May, June, July period on the left, going all the way out to January, February, March of 2021, or sorry, 2022 on the right. So you can see that throughout the remainder of this spring and summer, they are predicting neutral conditions with increasing chances of a La Nina event again as we move into next winter. Very low probability forecast right now for El Nino to occur. And I mentioned right at the top of my talk that you'd see this graphic again, and that's what you see here. So the purple line being where we've been in moderate La Nina territory, coming back out of it. This wasn't updated clearly since mid-April, but as I said, we're back into neutral territory. But if you pay attention to kind of all the spaghetti lines shown here, you see that a lot of the times when we have been in a La Nina, we tend to get a double dip La Nina. So a lot of years we're expecting to bounce back down. So, you know, when you go back here again, you see that that's what's shown in the model forecast. We've got a lot of predictions for at least equal chances for a La Nina as we do another neutral year. And then just looking at ocean temperatures as they currently stand as of last week, and this is using a different baseline. This is the 1971 to 2000 base, so of course a cooler time frame, but surface ocean conditions very warm across most of the Pacific. There are some areas of cooler than normal water along the coast of British Columbia and down into far Southern California. But overall, the North Pacific is 0.6 degrees C above this normal baseline. So just to wrap it all up, some key points. I think we've talked a lot about how the March and April time frame was just exceptionally dry, sometimes the driest on record for most of the Northwest. There are also long-term precipitation deficits in the region that have persisted over a couple of years, especially in that lower Columbia Basin in Washington, the Oregon coast, sometimes as much as 50 to 70% of normal. But the June, July forecast from the Climate Prediction Center is still showing higher than normal chances of above normal temperatures and below normal precip for all of our area, or most of our area, I'm sorry, for the summer season, which probably indicates that drought conditions are likely to get worse in the coming months. And that unfortunately coincides with elevated chances for increased wildfire potential throughout the time frame, extending into the fall. And this has all led, all these drought conditions have really just led to poor pasture and range conditions, reduced irrigation inflows. We had a pretty anomalously high number of spring fires that have occurred this year. And so folks are really starting to feel the impacts of this drought currently, and I think we'll probably continue to as we progress later into the summer. So that's all I have. I'm happy to try to answer any questions people may have.
Thank you so much, Robes. Just remember, remind folks, please put your questions in the chat box, and or you can raise your hand and I'll unmute you and you can ask direct. I know that was a lot to intake, like drinking from the fire hose of climate data. That was amazing. So I'll give folks a minute to put some questions in there. I do have one question for you, Robes, kind of bringing this to your expertise of working in river systems, et cetera. Have you seen any of this climate data and or kind of our water predictive forecast? I think we think of water a lot in irrigation supply, but have you seen this looked over to, let's say, water availability for fish habitat and passage, et cetera? And do you have any kind of concept of how this might impact that going forward, just based on your historical experience?
That's a good question. I think I have seen some analyses of those, and unsurprisingly, I think they really vary by site. In terms of water availability for passage at, say, main stem Columbia dams, I know those types of forecasts exist and certainly have an effect on both power production and fish passage. I've seen a lot of studies that have looked at what this might mean for fisheries and fish effects going forward, but I haven't seen a whole lot of retrospective analyses to look at how maybe drought thus far has affected what we've seen in terms of fish populations. I think that there's a lot more or greater understanding that the ocean conditions that our fish face tend to drive at least returns a lot, but I haven't seen a whole lot in terms of how watershed specific drought would affect those populations. But I think there's probably a lot out there, probably more than I know.
Great, thank you. Folks, just remind you, if you've got any other questions, feel free to put those into the chat box. Like I said, I know it takes a lot to assimilate this type of information and bring it to what do you do about it. And our next presentation actually starts to work into that about, how do we work on this from the output of the, let's look at it more from carbon sequestration and greenhouse gas modeling for increasing or decreasing impact to weather effects of snowmelt change, et cetera. But this one was very interesting, your presentation, and just looking at that forecast forward. And by the way, another question for you. So you clearly took a lot of time to find many different resources of data and bring that together. Are you aware of any singular source of data availability that's helpful in, let's say, someone who might want to follow this work over time, but is a bit of a novice and not able to pull all these resources together? Do you have somewhere you would recommend a resource or two that's most helpful?
Yeah, I guess the two that I feel like I fall back on most that are pretty easy to remember, one would be drought.gov. and that is a multi-agency effort, and they have a ton of resources on there that allow you to zoom into very small granular levels, or you can look at big picture, nationwide perspectives. So drought.gov really has a ton of great resources there. And then at least in terms of climate, I would say the Climate Prediction Center, the NOAA Climate Prediction Center is probably the other big one. And a lot of these sites, they tend to reference one another. So if there's information that's gathered by, say, a university or a consortium or a different agency, a lot of them are referenced from things like the Climate Prediction Center as well. So that's another good place to go for kind of a clearinghouse of information.
Great, thank you. And I just put both of those links in the chat for folks so they can capture those too. Well, with that, we have a lot of comments in here about great presentation, tons of information, very useful for folks. I have a feeling I'll be sharing the recording of this presentation out with quite a few people who may not be here about just this is a great way to look at this. And you watch out, you might have to be an annual presenter for us to give us the, the outlook for the year. So with that, Robes, I will come back on and just say thank you very much for this presentation and for being with us today. Really, really appreciate your time and efforts here.
Yeah, you bet. Hopefully the fire hose allowed you to at least have a sip and you didn't just lose it all. So
well, that's the beauty of the recording, right? I can just keep watching it until I, drink in all of the knowledge and information. I can get it all
the
in.
big picture is clear, but thank you.
Okay. Well, thank you so much, Robes. Really appreciate it.